What you are looking at is a poorly known yet highly unusual geologic wonder found within the interior of the nation of Yemen. Here, what almost looks like a whitish-brown tree trunk with roots is in actuality a massive rock formation. This formation is referred to as Damt and measures approximately 553 meters or 1,814 feet wide and 51 meters or 167 feet tall. Unusually warm water even for the desert of Yemen along with emissions of carbon dioxide also originate from this cone. While it might be a bit of a stretch to call the water within it a hot spring, water is emitted at a temperature of up to 45 degrees Celsius or 113 degrees Fahrenheit. While many locals consider this strange cone to be volcanic, this is only a partially correct assertion, as Damt is not a volcanic crater such as Amar, but rather a massive feature formed by the dissolution of underlying calcite and Arcos sandstone and a layer of marl, creating what is known as a Travertine cone. Before I discuss how this feature still relates to magmatic activity, I will first describe what exactly Travertine is. Travertine is a rock type primarily composed of calcium carbonate via the mineral calcite, which is distinguished by numerous layers. Unlike limestone, which is also a calcium carbonate rock, travertine often forms in hot spring or volcanic environments where it precipitates onto the surface as a layer of rock once amounts of elevated carbon dioxide within a hot spring's water escapes. This generally occurs in water temperatures ranging from 26.7 degrees Celsius to 93.3 degrees Celsius. The carbon dioxide release is a telltale sign that some form of underlying magma exists in the vicinity somewhere deep in the crust. This is because as magma solidifies or just sits around in the crust, it naturally releases fairly large quantities of carbon dioxide. Yet, to the best of my knowledge, we have never detected a nearby body of magma. Although 50 kilometers to the north there is a volcanic field which is presumed to be active as it reportedly produced an explosive eruption in 1937. Thus, it is clearly plausible that some form of a magmatic intrusion could have helped form this magnificent travertine cone. So, what is the conclusive evidence that carbon dioxide does have a magmatic origin? The answer involves trace elements detected in the travertine the cone contains. As unusually high levels of the elements arsenic, iodine, and most notably selenium were detected within the rock. For context, all of these elements occur in heightened abundances within low-temperature geothermal ore deposits, often directly above a solidifying magma chamber where they are in place due to the upward motion of gas and heated water. Selenium is considered to be the 10th rarest stable element in the Earth's crust, occurring at an average concentration of 50 parts per billion. Yet, in this travertine, selenium occurs at a concentration of 5.9 parts per million, 118 times higher than normal. Additionally, arsenic occurred at 46 times background, while iodine was 47 times background levels. Based on the reported geochemistry, these elements seem to have originated from the minerals orpiment, clausthalite, and laterite. These three minerals can form together, but only at a temperature between 100 and 130 degrees Celsius. Although the exact age of Damt is uncertain, one source suggested that it formed about 10,000 years ago. At the time, carbon dioxide-rich heated water rose upwards to the crust, having been heated by a still quite hot magmatic intrusion which stalled at presumably several kilometers depth. This heated water split into several pathways but primarily utilized small crustal weak points via faults. Reaching the surface, carbon dioxide was released, causing the calcium carbonate to precipitate onto the surface as layers, building a mound. As this mound had an irregular profile, repeated influxes of heated calcium carbonate-rich water caused runoff to occur primarily along certain low-lying points, which over time formed root-like ridges. Over several thousand years, Damt was constructed. The rate at which this cone grew was highest during its early years, as ever since then the heat from underlying magma has decreased as it solidifies. As for the circular crater in the center of the travertine cone, this formed due to ground subsidence when abundant groundwater disappeared during a particularly dry period. As a final note, I would like to thank my new patron Katie and Jasper for supporting this channel.